Hello students, as you all know, we are dealing with MOSFET in our previous videos. And in today's video, we will be seeing an effect called short channel effect. If you remember the base width modulation with respect to the bipolar junction transistor, this short channel effect is similar to base width modulation. And we will see what are the various effects due to the short channel in MOSFET. The short channel effect occurs in MOSFET when the channel length is comparable to the depletion layer width at the source and drain junction. Until now, we were not considering a depletion layer width at the junctions, the source and drain junctions separately. A MOSFET will have becomes a short channel device when the channel length is same order of or is in the same order of magnitude at the depletion layer widths at drain XDD and at source XDS. That is, the effective channel length, the total channel length is approximately equal to the source and drain junction depths. And this is possible when we try to reduce the channel length. And why we try to reduce channel length is by decreasing the channel length, we can increase the operation speed. As you all know, we want our device to act fast. And also, by reducing the channel length, we can also increase the number of components per chip. And because of these requirements, we try to reduce the channel length, and when we reduce the channel length, the short channel effect arises. And the short channel effect are attributed to two physical phenomena. What happens if the short channel effect comes into picture? The short channel effect imposes limitation on electron drift characteristics in the channel, or it will change the electron drift characteristics, and also it modifies the threshold voltage which was prevailing earlier. So due to short channel effect, we will get affected with the electron drift characteristics, and also the threshold voltage is varied. And this is occurring because a charge sharing happens between source and gate or drain and gate, which we were not considering in our previous discussions. We were just telling that the gate to source voltage was affecting the channel without considering the charge sharing between source and gate and drain and gate. This picture will help you to visualize the effect in more detail. Earlier, we had a rectangular channel beneath the gate or beneath the oxide level, which was the channel for the MOSFET. Now there is a triangle, red triangle being made on both junctions, the source junction and the drain junction, which changes the shape of the channel. Now it is not rectangular in shape. And this variation will affect the current flow in the device. The triangular region forming at the two ends, that is at the source and drain ends, changes the channel shape from the rectangular shape to a trapezoid shape. And due to this variation in the channel, many effects come into picture. The different short channel effects include channel length modulation, drain induced barrier lowering, which is also known as punch through, velocity saturation, threshold voltage variation. As I had mentioned earlier, there will be a variation in the threshold voltage, and hot carrier effects. We shall see these effects one by one in detail. The first effect, which is the channel length modulation. As we keep on increasing VDS, which is the drain to source voltage, as you all know, we want the MOSFET current or ID controlled by VGS alone. That is our ideal requirement. Now we will see, as we keep on increasing VDS, the region for which the inversion charge is 0 keeps on increasing. On keeping VGS constant, this is happening. And because of this, the channel length keeps on decreasing. This phenomenon is called the channel length modulation. This picture will give you a good idea. As you can see, the channel length is varied to from L to L minus L dash. Initially, the channel length was capital L. As we increase VDS, it gets decreased to L minus L dash. If you remember the base width modulation, this is similar. And since the applied voltage between drain and source VDS is affecting the channel length, it is affecting the current ID, and that is known as the channel length modulation, which is the effect of the short channel. The next effect is the drain induced barrier lowering. When the depletion region surrounding the drain at the drain end extends towards the source, and the two depletion layer merges, which means the XDS plus XDD. XDS is the depletion region at the source side, and XDD is the depletion region at the drain side. When it extends and merges, that it becomes the channel length. In that case, punch through occurs. What is punch through? In small geometry MOSFETs, the potential barrier, which is the channel, is controlled by the gate to source voltage VGS and drain to source voltage VDS. If the drain voltage is increased, the potential barrier in the channel decreases. So now the potential barrier is not only controlled by VGS, it is being controlled by VDS too. This reduction in the potential barrier eventually allows electron flow between the source and drain. Earlier it was controlled by the gate to source voltage, if you remember, which means the threshold voltage is lowered. And this current, the channel current that flows under this condition, even when the VGS is less than the threshold voltage, a current is being flowing. Such current is known as the sub-threshold voltage. If you remember earlier, we had to have VGS greater than VT for the current to flow. Now, due to the merger of the depletion layer, this happens before the VGS becoming greater than VT. This current is called the sub-threshold current. The next effect due to the short channel is the velocity saturation. The charge carriers move with a particular speed, which is the velocity of charge carriers. As you all know, the charge carriers could be electrons or holes. And this velocity is proportional to the applied electric field. That also you know. But this dependency on electric field alone is valid only for small fields. As the field gets stronger, the velocity stops increasing, even if we increase the electric field, or it saturates. That means at a critical electric field, they tend to stabilize the speed. Even after increasing the electric field over this critical electric field, the charge carriers cannot move faster. This is called the velocity saturation. And this is specially seen in short channel MOSFET, because they are having higher electric fields. So the dependency of the drift velocity can be mathematically said as the VD. The drift velocity is equal to mu E by 1 plus E by EC, where mu is the proportionality constant and EC is the critical electric field. And the electric field E is equal to the applied drain to source voltage VDS divided by L, which is the channel length. As the channel length is smaller, or in short channels, this is the case. This will depend on the electric field and the critical field. It becomes constant. But in case of normal MOSFET, this equation becomes VD is equal to mu E, which depends just on the applied electric field. So it will be linearly increasing. But in case of short channel, this saturates after the critical electric field. So this is another effect due to the short channel. Next is the threshold variation. This we had pointed out earlier too. The threshold voltage is normally a function of the applied body bias, VSB, body effect, that we had discussed, which is an outspring of the manufacturing technology. But as the device dimensions are reduced, this threshold potential also becomes a function of L, the channel width, length, channel width W, and also the applied drain to source voltage. Since a part of the region below the gate is already depleted, since we are considering the depletion at the source and drain sides, now the threshold voltage is reduced, or the voltage required to get the strong inversion is smaller, which means that, in other words, VT decreases with L for short channeling. So it is a function of the channel length. Another effect due to the short channel in MOSFET is the odd carrier effect, which is different from the other effects that we have discussed until now. This problem is caused by hot electrons. Hot electrons means high energy electrons, which is having that much energy so that they can enter the oxide layer. And this hot electrons gets trapped in the oxide layer, and that will start charging the oxide layer. And as the time moves forward, this hot electrons will degrade the device performance. How it is degrading? It will increase the threshold voltage. Now the MOSFET will function only for a higher gate voltage. And besides varying over a design, threshold voltage in short channel devices also have the tendency to drift over time. So this variation in threshold voltage will affect the performance of the MOSFET. And this is due to the hot carrier effect. The hot electrons, which is high energy electrons, which is entering to oxide and getting trapped, will start charging the oxide layer. And that will increase, in turn, increase the threshold voltage requirement. So these are the effects due to the short channel. Short channel is due to our efforts to reduce the size of the or length of the channel. Why we are reducing the length of the channel, or why we are interested in reducing the length of the channel? We need a faster device, and also we want more devices, more density of devices coming into the same chip. But that is having side effects. That side effects are called the short channel effect. Thank you.